Now let's talk about the finite difference equation. This is in the chapter on two-dimensional steady state. But I'm going to first solve a one-dimensional steady state problem and introduce you to the problem. So this is the problem. We solved it before in the previous chapter. We have a pin or a round wire, okay, and it's connected to a base on both ends. And that base on both ends is given TB and TB. Okay. And we pass electric current through that wire, and it has some resistance. So what do we get? We get some ohmic heating, some electric resistive heating in this wire. And we characterize it by Q dot. What is Q dot again? Watts per meter cubed. That's our rate of heating per unit volume. Okay. And this wire has a thermal conductivity K, has a diameter D. TB and TB are the same. And you have fluid over here. It's providing cooling. So this is T infinity with convection H. Is the problem going to be symmetric about the middle of the wire? Is the temperature profile going to be symmetrical? Yeah, now if TB1 was different than TB2, then it would not be symmetrical. But if the base temperatures are the same on both sides, it's symmetrical. And so we're going to actually assume that TB1 and TB2 are the same, and they're actually the same as T infinity. That's the problem that we had solved already a couple days ago. And so we introduce a coordinate system, x, and we'll let x run from 0 to L. And we're able to get an analytic solution for this problem. What did the analytic solution to this problem look like? Well, the analytic solution was the temperature at any location x going from 0 to L, is equal to the T infinity, the fluid temperature, also the temperature of the end of the rod at L, minus Q dot divided by Km squared times our old friend cosh of mx divided by cosh of ml minus 1. Let's take a look at this for a minute. Do we understand each term? Do we understand the Q dot? Sure. The K, thermal conductivity? Sure. Oh, what about this m squared? Well, that m squared is h p divided by k a sub c. For a round rod, maybe you've done it enough times, that the perimeter is pi d. The cross-sectional area is pi d squared over 4. So the perimeter divided by the cross-sectional area is 4 over diameter. So you could replace it for a round rod, h, 4 divided by k d. So that's what the m squared is. And then the square root of m, square root of m squared gives us m. And then we understand what x is, we understand what L is. So without any numbers, there's our analytic solution. So what we're going to do is we're going to pick some values. We'll pick the diameter is going to be 5 millimeter. The length will be 20 centimeters. The thermal conductivity will be 200 watts per meter degree C. The convection coefficient will be 50 watts per meter squared degree C. And our Q dot is 5 times 10 to the 6 watts per meter cubed. T infinity is 25 degrees C. And so there you go. But now let's solve this problem numerically. How would we solve this problem numerically? One of the first things you do is discretize. You introduce nodes, and you have regions identified with each node. So you can put a node right there, and you could put a node right there. That's 2 nodes, but we want more nodes because we're only going to get the temperature at nodes. We're not going to get the temperature at all locations. The analytic solution gives us the temperature at any x in our region. X goes between 0 and L. But now we're just going to go there. And so there'll be a node here, node here. Let's not get tricky. Let's just have equal spaced nodes. And you think about it, you have to make a choice. If we call this node 1, and that's node 2, and that's node 3, how many nodes am I going to have? If I said we're going to have 11 nodes, then what is the spacing? This spacing is called dx, delta x. dx is either going to be L divided by 11, or L divided by 10, or L divided by 9, or L divided by 12. So that was a pretty easy question. Everybody got it. It's not this one, it's not this one, it's not that one. Delta is L over n minus 1. And if you had 11 nodes, 11 minus 1 is 10. Boom, away you go. All right, so that's our delta x. Okay, so the idea is you introduce nodes, and now we know where they're at, and we know the separation distance between them. What we want to do is write an energy balance. We don't ever get away from the conservation of energy. An energy balance for each node. And you can do it for a generic node, or you can do it for one node in particular, either one. But what we do is you come in and identify some volume associated with that node. So let me go to another slide. And we have, I don't know, how do you want to work? Do you want to work it with the I plus 1, I minus 1? Or do you want to work it with the particular numbers? So this is a node, there's a node, there's a node. So a lot of times I'll work with, well, here's node I, here's node I minus 1, here's node I plus 1. And you have conduction down the axis. Okay, then you have conduction down the axis. You have convection out, and you have, I'll just draw it a little different, generation, heat generation term, G-E-N. So conduction, convection, and generation. Those are our 4 terms we need in an energy balance for each and every node. What was the distance between here and here? Delta x. So the distance from node to node is delta x, but it's also the same distance from face to face of a control volume for a particular node. Hopefully I'm emphasizing the obvious. But now let's write our energy equation. And when I write the energy equation, what I'm going to do is what I recommend is when you write these, you write them for everything going into a colder node and everything around it mathematically is warmer. Just think about that for a minute. Just turn it around. Instead of having some of the conduction out, just put all the conduction in. Let me try and fix that. And the convection, instead of making it out, make it in. So then I have just the sum of all ins equal to 0. Everything's in. How do I write it mathematically? I personally think about the node that's the focus. I'm doing an energy balance for node I is cold, lower temperature compared to all the other nodes around it. So if that's true, then what is my conduction going in from node I minus 1? Well, it'll be temperature I minus 1 minus Ti. That's my driving temperature difference. And because Ti is lower, I want a positive delta T to drive it in. So I write it Ti minus 1 minus I. Okay. Then I multiply by K, the cross-sectional area for conduction, divided by the distance. Okay, let's go to the next conduction in. I'm going to write it Ti plus 1 minus Ti. That'll be a positive temperature difference driving the flow into the node. I'll have a K, A sub C divided by delta X. All right, let's do the convection. T infinity minus Ti. Isn't that a positive delta T if I think about Ti being low compared to all others? Yeah. And then I'll have an H, but I have to have a convection area. That's going to be my perimeter. times delta x, isn't it? Isn't that my convection area, perimeter, moved along a distance delta x? If you wanted to, you could substitute for that perimeter pi d. No problem, go ahead. Just like we could substitute for this cross-sectional area, pi d squared over 4. No problem. Okay, then the last is my generation. Okay, well, what were the units on Q dot again? It was heat generated per unit length, per unit area, or per unit volume? Per unit volume. So I have to multiply by a little volume. Well, what's my volume associated with that node? Isn't it my cross-sectional area times delta x? Will that give me a little volume? Is this same cross-sectional area, this one, the same as that one? Are they the same? Yeah, they're the same. Now I've got them all. I put an equal sign. When I have the true final steady state temperature distribution, that equation is satisfied. I'm looking for the unknown temperatures. So in each of these equations, I typically will have 3 unknowns in one energy balance equation. So what I'm going to get is a coupled system of the equations. They're going to be linear algebraic equations. Maybe I'll get 10 equations, 10 unknowns. I'll have to solve them. All right, we need to do it for node number 1, and we need to do it for node number 11. Let me go back. Where is node number 1? Right there. Where is node number 11? Right there. You don't even need the energy balance equation. So for node 11, it's kind of trivial. You just say, oh, node 11 is equal to T infinity. And for this problem, that was 25 degrees C. Done. I really don't need an additional equation for node 11. That's my equation for node 11. It comes from my boundary condition. But I do need to work on node 1 a little bit. So where was node 1, especially in relationship to a control volume associated with node 1, and then here's node 2. So this is node 1, that's node 2. Look again at this mesh here when I cut it. If I say, okay, this is for node 2, I go halfway between 2 and 3, and halfway between 1 and 2 to get that for node 2, right, like that. How much do I have for the volume of node 1? Do I have the same amount as for each of the other nodes? Or do I have half of it? I got half of it. So let's spend a little time because you'll make errors on this one. So what is the distance here for the volume associated? It's dx divided by 2. But is the distance between node 2 and the distance between node 1, is that dx divided by 2 or delta x? Which one is it? It's delta x. So right away, students will get tripped up. How come you divide by 2? Because the volume associated with 1 is half of what it is for the other nodes. Okay, now, so when we write our energy balance, we'll have K times, well, let me do it over here. I'll have K A sub C divided by delta X times T2 minus T1. That's kind of parallel with that one. And then I'll have H P delta X divided by 2 times T infinity minus T1. I can see this stuff is now in my way, so I'm going to move it out of the way. Get that over there. Just not needed. And then I'll have Q dot A sub C. Is A sub C the same? Or has the conduction cross-sectional area changed? It's the same, isn't it? Times delta X divided by 2, but the volume's half. That's equal to 0. So there's my energy balance for node 1. Did you have a question?
Yeah. There's only one conduction because
That's right. So kind of put a hashed area back on that side, insulated,
okay.
adiabatic, symmetrical. Yep.
Okay.
That's right. So now we're going to jump over to Excel. Wish me luck, right? Anytime you do a live demo of any software. Huh? It breaks. Yeah, you know me. So we're going to solve this problem. What I need to do is I need to put in things like conductivity. And I'm just going to put them in, and sometimes I'll put units like watts per meter, C. And for this problem, our thermal conductivity was 200. Hey, is that closer to steel or is that closer to aluminum? Aluminum. Hey, you're learning. You're getting good. All right, and then we have a convection coefficient. I'm not going to type in the units. We know the units on the convection coefficient. It was 50 for this problem. And then we'll have a diameter. And we give it in millimeters, but we really want to put everything in meters. So the length was 0.2. Q dot, and Q dot was 5 times 10 to the 6. Will that work? We also can start calculating things. Perimeter, what was that equal to? Pi times then our D, true? And then we put it in our cross-sectional area. That's going to be pi times D squared divided by 4. And if you want to check it, perimeter, or we're going to use perimeter divided by the cross-sectional area. Perimeter divided by cross-sectional area. And then you can check that to see if that's equal to 4 divided by D, which it should be. So that's 4 divided by D. And if it's not, we made an error. Good. Looks reasonable. All right. And then we're going to put in things like, I'll put them down here. The number of nodes is 11 for this problem. How about the number of divisions in this problem? Equal to n minus 1. We can now come in with 31 nodes, and you see how it updates? This is the beauty of it, isn't it? You can update things pretty quick. Anyway, so I'm going to calculate what is dx. Dx is equal to L divided by the number of divisions, and away we go there. Okay, now I'm going to calculate the analytic solution as well as the numeric solution and then compare them for this problem. Okay, well, what was the analytic solution? There it is. And so we have the analytic solution to this problem, and I'm going to compare it with the numeric now, hopefully, without embarrassing myself. So what I need to do is I need to calculate that parameter m. Hey, what was that parameter m? The square root of h times perimeter divided by area divided by the thermal conductivity K, close parenthesis, there's m. And then you can calculate ml as a parameter, which is simply m times our length L. And then we had our, I'm just kind of putting these in T infinity. In degrees C was 25. T base in degrees C was 25. And we're going to have, for our numeric solution, we're going to have K times the cross-sectional area divided by dx. Let's put that in as a parameter. K times the cross-sectional area divided by dx.
You never changed the number of nodes?
Back. I'll change it back right now then. 11. There you go. And then we're going to have the h times the perimeter times dx for the convection. So we're going to have the convection times perimeter times dx. AC times dx. Cross-sectional area times dx. That's for the volume. And then last one, I can put it up here. I think I needed it, is q dot divided by k divided by m squared. So that's a little extra. Okay, so what we pick up is we pick up Q dot, I'm about ready to do it, divided by K, divided by M squared. 125, very good. So what I would do is I'd introduce nodes just to help you. 1, 2, 3, 4. I could have done that faster, but hey, right? You know, I've learned a lot of tricks, Excel tricks from students. They come up to me later, hey, let me show you something. You're pretty clumsy here. And I learn. I really benefit from that. So thank you if you're thinking that right now. All right, so we have x starts at 0, true? So this is my location x for each of the nodes. And then this will be this one plus my delta x. And I'm going to put a F4. I'm fixing that. And so when I scroll down, it won't change. Grab that lower corner. Whoops, I didn't grab it that well, did I? Grab that lower corner, drag, and verify that that's L. True? All right. So that's my location X. Maybe tighten it up a little bit. Now, what is my T analytic in degree C? Well, that equation is not all that pretty, is it? But the equation says, go get T infinity, right there. When we drag that equation down, we won't want that cell changing, so we'll lock it in with the dollars, right? $F, $5. Then we're going to subtract Q dot times K divided by M squared, lock that in, times in parentheses, in the numerator, cosh, oh, don't you like it when they have a built-in function? Cosh of the function m times, and I forgot to lock that one in, whoops, m times x, so I'm just going to go over here and hit that, perfect. And then close parenthesis, divided by cosh of m, lock that in, times L, well, I already had that, don't I? Just put ML right there. Close parenthesis, minus 1, close the overall parenthesis, and let's see if it works. Here we go. That's a number. Take that formula, drag it down, and it looks like we have too many digits. Clean it up a little bit, and I can click on this cell, kind of check it. So there's the analytic solution. But the purpose is not to implement the analytic, it's to actually implement the numeric. So we're going to be looking for the temperature numerical. There's a number of ways to solve it, but I'm going to just say guess it and then use solver, which is built into Excel, to solve for it. Let me scoot this up a little bit. All right. So let's go ahead and just start guessing. Let's say it's we guess it's 90. And then I'm going to guess, oh, it's 86. You just have to populate it. And don't have to be a very good guess either. Let's might as well. You said it doesn't have to be a good guess, Professor. You know, here's some garbage. Garbage in, garbage out. But we better satisfy the boundary condition. All right. So what we do is we come up and we say, for the first node, that's always the most difficult, because it was a special control volume. But the other ones, you just look at your equation. How did we have to implement that? Wasn't that energy balance? The first is our K, A sub C divided by delta X. That's one reason I populated that. Put an F4 there, times the temperature at node 1 minus the temperature there. Does that look like my first term in that energy balance? And then we add to it the second term, same K, A sub C divided by delta X, times this temperature, temperature 3, minus temperature 2, plus we have the perimeter convection, put an F4 on that one. You know, I forgot to put an F4 on this one to make it locked. All right, keep going. Times our T infinity, right there, lock it in, minus our T2. Is that T2? Yeah. And then the last, we add our Q dot, which is way over here, times the volume. Volume is A sub C times delta X. I need to lock that in and lock that in. And when I hit 0, I hit return, it doesn't equal 0, does it? But if I had the right temperatures there, it would equal 0. So this energy balance, I can drag it down, and I need to balance the energy for those nodes. And I just double check, does that look reasonable? Looks reasonable. Now I have to come up and I have to write the energy balance for this node. So that's equal to the conduction times this temperature minus temperature 1 plus the convection times this temperature T infinity minus temperature 1 plus the one thing I forgot is I have to divide that by 2. And then the volume divided by 2 times Q dot. Where is my Q dot? There it is. All right, I'm going to pause. Does that look okay, that equation, or did I make an error? You're probably pretty sharp following it. Does it look okay? All right. So now I want that to be 0. So what product? This is going to be this term squared. And then you just drag that formula down. And then you want the sum of all of those here to be equal to 0. But it's far from 0, isn't it? And so what am I going to show you at the next point? Somebody knows. So we all go under the data tab. And way over here, if you haven't built it in and used it, solver. And right here it says, oh, I already highlighted M13. And I want to minimize it. I want to drive it to 0 by changing, and this is the slick thing about solver, I can change those cells. Don't change 25, but you could change all those cells. So hopefully that makes sense. Hit solve, cross your fingers, and you can reject the proposed solution or you can accept it, and we'll hit OK. We'll clean up some digits. And this was our numerical. And this was our analytical. And what do you think? So whenever you have a chance to check your numerical implementation with the analytic solution, you want to do it. So, oh, how did these change? Yeah, okay, let's do that again. Let's go up to Data tab, over to Solver. And because I had selected it before I went to the Data tab Solver, it says, okay, I think you want to handle something in M13. Yeah, that's where I have it. And I went in here, and this was originally blank. And I said, I want to not maximize it. I could set it to try to set it to a value of 0, but minimum is the same thing, drive it to 0. And by changing, and then I just went over here and I selected all of these. When I selected them, it filled that K2 through K9. And then, again, I have played with constraints. I've used them. They're very good when you need them. But at this point, you don't need anything. And then you just hit solve. Now, you can set this up as a big matrix, AX equal B. And Excel has the ability to do AX equal B, but it kind of peters out at around 20 by 20 because it's huge. I mean, it's just big. And they're actually going to invert the matrix, which is kind of stupid. I just want the solution. I don't want the inverse to the matrix. I just want the solution. And so Most linear algebra solvers don't ever invert the matrix. They just get the solution. That help? All right, I'm about ready to leave it unless there's any other comments, questions. Should I save it? No, it's garbage. I'm going to save it anyway. Okay, September 19th in the PM.